science, especially in renewable energy research. So we had our first talk by Professor David Kahan from Israel. And talented scientist among us, and to listen to his talk and research on the topic passive and dynamic defects in perovskites. Dr. Aditya, do we have your permission to record the session?
Yes, yes, go ahead. No issues.
Okay. So thank you very much for accepting our invitation. Please take over your stage.
Oh, thank you. Thank you, Anjani, and the Dean for the kind invitation that you extended. It's a pleasure to give a talk at this forum. So my name is Aditya, as Anjani just introduced, and I have just joined SENS in Indian Institute of Science, and I'm currently just building the lab, and also most of this work is something I've done previously, and some work which has happened in ISC. So the topic of today is essentially about passive and dynamic defects in perovskites, and we'll go through a bit around it. But before we go there, let me introduce the place where I work. It's actually closer to you guys. So, SENS, the Center for Nanoscience and Engineering, is like a national hub for all nanoscience related activities. And it is a center which is open for all, which means that a person like me or a person working with me or students like you or professors sitting around, everyone has the same set of access or same rules of access as, I mean, the faculty where I am sitting. That's what it is. Inside the department, we basically have two separate sections mainly. And these sections include a very big clean room, which is around 14,000 square feet, which has both class 100 and class 1000 clean rooms. And this is for doing all advanced nanofabrication that you can think of. And beyond that, once you have fabricated, you would like to characterize a lot of things. So we have a 7,000 square feet semi-clean room for doing a lot of characterization related activities. And both of these are national facilities, so you're welcome to browse the website and get to know the details of how to access these facilities if you wish to. And we actually in the department work very closely with industry, and there are a lot of industries who are affiliated with the department to develop not just technology but also to sort of see how we can interact with industry and come up with new ideas, okay, and potential solutions. The research focus at the center itself is on these topics that I have displayed here, starting from gallium nitride based power electronics. It's a big push at the center at the moment, given the electric vehicles, boom that is happening at the moment. We also work a lot on photonics, emerging electronics, nanobio healthcare, photovoltaics and energy devices, which is one of my research areas, and talking about agriculture and environment based on sensor technologies. Okay, and a big push in the department, which is a very unique set of expertise and capability, is to basically do scaling along with packaging. So at Sense, what we do is we don't just start with a piece of silicon wafer. We make the device, we basically go all the way up to a fully packaged device, which we can sell directly to the customer. Okay. For example, one of the customers is Hindustan Aeronautics. They use the pressure sensors manufactured at Sense in helicopters which fly in Kashmir and all. Okay, high altitude flying helicopters. Okay, having said that, let's get into the topic of today. So, perovskites, I think you guys are already used to this word, and the seminar series is associated with this. So, I'll not be introducing too much in depth. But the question which, for people who are aware of this field, is that is it an ideal semiconductor? Okay, so that question is something which is open-ended. There is still no answer to it. But yeah, it's very interesting to sort of see properties which are ideal in nature, but there are also challenges in terms of what are the shortfalls in perovskites. Okay, we'll go through it a bit in terms of defects too. So, perovskite, in brief, is a crystal structure class, and it's a big family. There's no one material. There are like numerous combinations, and I think we have only discovered few of them, not many. Many discoveries are yet to be made in this field. The main perovskite, which is of a lot of interest for the scientific community, is having a structure of ABX3. Okay, where A is a monovalent cation like methyl ammonium, B is a divalent metal like lead or tin, X is halogen, either iodine, bromine, or chlorine. Okay, fluorine doesn't fit into the structure, so that's why we don't hear much about fluorine-based perovskites. So, if you consider these three typical cations and anions, you can basically form a methyl ammonium lead triiodide. Okay, so this is a typical perovskite with a tetragonal structure as depicted here. Okay, but there is as I said, it's a big family, and that family doesn't just include the ones which have a formula of ABX3, but you can also extend that, and you have something like this, as I'm displaying on the screen at the moment. So you also have families which have three-dimensional perovskites, which are connected in all three directions, which means the charge transport is possible in all three directions. Okay. We also have two-dimensional perovskites where the charge transport happens only along one plane. Okay, it's a 2D charge transport. The difference between these two is the red cation here in the 3D structure is very small. For example, methyl ammonium, which I just showed you in the last slide, is sort of a smaller cation. It helps in forming a 3D perovskite, like methyl ammonium lead triiodide. But if that cation becomes longer in the sense if you have more than 3 carbon atoms or beyond, you basically end up separating the lead iodide sheets. And this separation leads to a 2D perovskite formation. Okay, so the charge transport only happens in one plane. So these are different famous kinds of families of perovskite, but there are more kind of perovskites, like one-dimensional perovskite, zero-dimensional perovskite, and so on. Okay, so the topic for today is about a different thing. I'll explain to you in the next slide. But going further, like something interesting about perovskites was just the numbers. But nowadays we are actually moving into the maturity phase where we are talking about the technologies being developed, not just in the lab, but actually moving towards industry. And the reasons for that are obviously the numbers, the attractive numbers that these materials actually end up giving in various devices. So the first one being you basically have very high absorption coefficient. So you absorb a lot of light in very thin film. Okay. So absorption coefficient is quite high. I mean comparable to gallium arsenide if you like. The power conversion efficiency, which is PCE, for solar cells was around 10% in around 2012. We are currently in 2022, so it's been 10 years, and within this last 10 years, the power conversion efficiencies have gone beyond 24%. Okay, and in context, to put it in right context, 24% is very close to what you get even in single crystalline silicon solar cell. So you achieve around 25-26%, and you're very close to that. Okay, and this despite the fact that this material is solution processed at low temperature. Okay, the temperatures you need to heat this semiconductor to is as low as 100 degrees, whereas if you talk about making silicon, you make it around 1000 degrees plus. So there's a huge difference in terms of how much energy you put in making this and what efforts go in making this. Although still being polycrystalline, this material shows very good performance. It not only shows a good solar cell performance, it also gives good LED performance. And the reason for that is the high PL quantum yield. So almost more than 70% of carriers can recombine radiatively. Okay, so you have only 30% of non-radiative loss. And this is for typical perovskites, but for perovskites which are specifically made for LEDs, like nanocrystalline versions, those can approach almost 99% PL quantum yield. So hardly any loss in terms of non-radiative relaxation. So the examples of few LEDs glowing are sort of shown here. People have also made lasers out of this. This is one of the examples of very thin laser being made. It's optically pumped laser, not electrically pumped, but people are working towards that because there is hope in LEDs, and that eventually can lead to a laser application later. The other interesting fact of all these high numbers and attractive performances is that it has very low disorder. Okay, so when you measure disorder using different techniques, you end up getting values which are extremely low and surprisingly low for such crudely processed semiconductor. And moreover, the band gap tunability in this family is very excellent because all you need to do is change some halogens or change some cations and your band gap is different. It's very different than what you do in MB grown 3.5, 3.6 or 2.6 heterojunctions. Okay, so all the indium gallium arsenide or things like that. So it's very easy to grow these materials, and it's very easy to even tune the band gap just by mere changing of few components in the solution. Okay, so going further, we'll talk about a bit of passive disorder, and the topic for that is graded heterojunction perovskite solar cells. So recently we did a work where we basically quoted a 3D perovskite. Okay, it's a 3D perovskite with just iodine as one of the halogen. And then what we did was, in order to sort of passivate the surface defects, because we believed there was some surface recombination happening, what we did was we grew another large band gap perovskite on top of this low band gap perovskite. Okay, the large band gap perovskite had a gunadinium cation. It had a different cation, and that actually ended up giving us a sort of an epitaxial layer on the top, if you like. There's not much difference in the morphology as such, but we found that the strain in the crystal structure was less, where we basically coat this surface treated sample here, and that basically resulted in lower disorder. Now, how did that be measured? It's basically from here. If you look at the bottom right graph, if you focus on this graph here, this is an absorption measured for all three samples, which if you focus on the control sample and the blue sample, which is basically the sample having this gunadinium layer on the top, the large band gap perovskite. What we find is when we compute the disorder is computed as the inverse slope of this absorption drop. Okay, it's called Urbach energy. And Urbach energy gives you a qualitative value of how disordered your system is. So when you compare the disorder in your two systems. One, your control system, where you had some surface defects, and the one where you basically passivate it using large band gap cation. You see that the Urbach energy reduces from around 16 to 14. Okay, so there's almost a 10% reduction in the Urbach energy, and this reduction is actually reflected in the defect passivation effect in the solar cell. So when you make a solar cell out of these two set of perovskites, this is the structure that we used for that solar cell. What we find is the main effect of surface recombination basically is to reduce voltage. And when we passivated that surface recombination effect, we can see an increase in voltage. So you can see a control sample with a voltage of 1.1, and we achieved voltage of around 1.2 volts for the passivated sample. Okay, and this 1.2 volts was back then state of the art number for a single junction solar cell made out of perovskite. Okay, so now we basically also see that the voltage differences are very clear here as well. We also see that the performance of solar cell was quite stable when you passivate the solar cell, okay, as compared to what you get in a control sample, which is unpassivated. So in the unpassivated solar cell, you can see the efficiency sort of drops with time, but that's not the same case with the passivated solar cell. Sorry. The other interesting thing, again, I told you about the voltage that you achieve in this solar cell. And you see this voltage is not a transient natured voltage. It's quite stable. And we observe the 1.2 volts is quite stable over time as well. The same is the case with control. So this indicates the clear shift in the voltage once you passivate the surface defects. So this is what I call passive defect. Okay. Now we'll talk about the dynamic defects, but before that we'll talk about band gap tunability in perovskites and something about photostability. So, so I told you that it's very easy to tune the band gap in perovskites, and how do I do it? In this case, I basically have a methyl ammonium. So this is CH3NH3 and lead as a divalent metal. And the three halogens are basically comprised of iodine and bromine combination. Okay, so I have the tunability between these two. What happens when I tune the composition between iodine-rich perovskite to a bromine-rich perovskite? You basically see that as you decrease the content of iodine, so let's say you had 100% iodine, no bromine at all, you have a band gap which is around here, 1.6, 1.5 eV in this range. Okay. As you decrease iodine and add bromine to the system, your band gap increases. So you start blue shifting your absorption curve. And this is very monotonic. As you see the composition, I keep reducing iodine, go almost to 0% iodine. I end up with 100% bromine. You see that the band gap is quite high for the bromine-rich perovskite. Now, what happens when you have such a case and you make solar cells with all these semiconductors is you basically end up getting reduction in band gap at the same, increase in band gap at the same time you reduce your photocurrent. Okay, so this reduction in photocurrent is proportional to this increase in band gap. Why does that happen? Because you absorb less solar spectrum and hence you generate less photocurrent. But at the same time, it's not just the photocurrent that reduces. There is also something else that happens, and that is increase in voltage. So as you increase your band gap of your perovskite, you also should simultaneously see an increase in the voltage in your device. So we do see a decrease in photocurrent with unexpected lines. But if you notice here, what we see is the voltages are not really increasing. Okay, they are sort of moving around the same value, more or less. So if you focus there, you will see voltages are sort of stuck. You change composition, while you increase or decrease iodine, the absorption is monotonically shifting. Okay, there is no peculiar bunching up as such. But when you see photoluminescence, what you see is if you have pure bromine samples, you have the photoluminescence here at around 550 nanometers. For pure iodine samples, you have it around 800 nanometers. But for all the other samples, the bunching effect is there. There is no monotonic tuning effect as such. So we were very curious about this and we wanted to investigate because these systems are used for tandem solar cell applications. Okay, and with the band gap being increased but the voltage being stuck at one point, you really cannot get efficient solar cells out of this. So we wanted to investigate the reasons behind it. So that brings me to the topic of dynamic defects. Okay, so we'll talk about it a bit here. So this is a busy graph. So if you focus on my pointer and just go through that part, I'll explain to you what it means. So this is an absorption spectrum. So you have absorption on the y-axis plotted on log scale. So it's very sensitive absorption. Typically, the absorption you see is plotted on a linear scale. Like 0 is at the bottom, then you have some other numbers at the top. But here it's on a log scale, so it's quite sensitive. So you're measuring quite low absorbances here. Now, what we find is for this black curve here, so when you see that you basically have this hollow dotted lines, you see that is the absorption when you basically measure before any illumination of the sample, okay, solar illumination. When you illuminate the sample with solar light, you measure the absorption as a solid dotted line, which happens to be the same as the absorption without any solar illumination. When you remove the solar illumination, you see that there is no change in the absorption. It's the solid line. Okay. So for pure iodine-based perovskite, your absorption doesn't change. And the same is the case with pure bromine-based perovskite, which is the pink sample here. Okay. But in between, where you basically had a mixture of iodine and bromine, where x equal to 0.4 for this red sample, and x equal to 0.4 would give you around 40% bromine and 60% iodine in the perovskite. When you have such a sample, or you have x equal to 0.6, where you have 60% bromine and 40% iodine, what you find is the absorption before any solar illumination, the sort of hollow dots that you see is following this trend here. Okay. When you illuminate the sample with solar illumination, under solar illumination, the absorption is red shifting. Okay, so this dotted line that you see is red shifting, and they are sort of having the same edge, almost the same absorption edge. Then when you remove the solar illumination, the absorption shifts back, which is the solid line, the solid red line or the solid green line. So what we observed was that under solar illumination, the band gap was red shifting. And okay, and this we had a separate absorption edge here, other than the absorption edge that we see here or here. Okay, this absorption edge is not possible to measure in normal absorption spectra. You have to measure it very sensitively. For this, we have special techniques, and that is what we use to measure this absorption. On the same lines, when we measure the photoluminescence, what we find is when we don't illuminate the sample much on the background and we excite the sample with very low laser intensities, we can get the PL in the place where it was supposed to. Okay. And when we increase the duty cycle of the excitation, means we are sort of simulating the solar illumination case, the PL red shifts. Okay, it shifts to lower energy and bunches up here, which is corresponding to the same band edge which we observe here. Okay, so we went ahead and studied this effect and trying to observe what happens or what's the reason behind this and what causes it and how can we learn a bit more about it. Because if we can prevent it, then we can make very efficient tandem solar cells with perovskites. So the focus of the next few slides is this region here, where you form these sort of unwanted states, which I call defects, and they form dynamically. So when you have light, they form. When you remove light, they go back. Okay, so that's the dynamic nature of it. Now, we not only studied photoluminescence, where we observe the drop in PL upon solar illumination and increase in the defect emission. As you can see here, this is where the PL is supposed to come originally, from the mixed halide perovskite, which has, let's say, 80% bromine, 20% iodine. What happens is the the PL actually from here reduces over time when you illuminate it with solar illumination, and the PL at infrared, which is here, keeps going up. Okay, this is the emission from the defect, so-called defect. Now, when we plot the time versus increase in PL, okay, which is the blue curve here at the bottom right, this is what you get. Okay, this is the time that it took for the PL to increase and stabilize at this point. When you compare the same with the XRD peak, okay, even when you measure XRD at around 2 theta equal to 29.65 for this perovskite, you see that the XRD peak also shifts, and that shift is happening and it is also stabilizing at the same pace as which the PL is increasing and stabilizing, which indicates that this PL shift is sort of also coupled with the structural change in the perovskite. So there's something structural that is changing in the perovskite under solar illumination. Okay, they follow the same kinetics. We went ahead and did some other interesting experiments. If you focus on the top graph here, we take a perovskite which has 40% bromine and 60% iodine, okay, which has this PL shift. Now what happens is, if I use three different excitation wavelengths, so I'm basically using, so let's say this perovskite has a band gap of around 1.95 eV. Okay, so this is the band gap. Any excitation above it, it will still absorb, and you expect to see the same effect as such. But it's not the case. What happens is, this increase in the PL from the low energy state and its saturation happens at different pace for different excitations. Okay, this time is shown here. So if you excite very high above the band gap with a high energy laser, you basically see that the excitation, let's say the PL increase at defect and saturation happens very fast in 4.6 seconds. If you excite it slightly lower energy laser, 2.33 eV, you basically see the excitation and relaxation is happening at a slightly slower pace, 25 seconds. If you excite the perovskite resonant with the band edge, so let's say the band gap is 1.95 eV, you excite with the same energy laser, you see that the time for stabilization of the defect emission is taking very long time. It's around almost 1 minute. Okay, so this is telling you that in all these cases, the point to remember is you are exciting with the same number of photons. So at end of the day, you are going to create the same number of electrons and holes with all these three excitations. The only difference is that in the excitation with this blue laser, which is 2.75 eV, you are creating a high energy photon, high energy electron hole pair. So you will observe thermalization of the carrier down to the band edge. That thermalization, which is phonon induced and is coupled to the lattice, is then interacting with this sort of defect formation. Okay, so the phonons or the excess energy you put into the system is also responsible for the faster defect formation. So it has a role in it. Okay, so if you only excite with resonant with the band edge, there is no excess energy, and you can see the defect formation is much slower. Okay, but you cannot excite your solar cell with one wavelength. You have to excite with the whole spectrum of sunlight, and hence you cannot prevent this effect from happening. Okay. The other interesting thing that we observed is in the bottom graph here. So if you focus on the red curve indicates the PL from the defect state. Okay, so you excite your sample with a laser from one side, the defect PL increases. This is what I showed you in the other slide. This is what I showed you here as well. The defect PL increases and saturates. At the same time, the PL from the main emission peak reduces. This is same as this. The PL from main emission peak reduces, PL from defect increases with time. Okay, so this is in line with what we observed till now. But what happens interestingly, if you excite the sample from both sides of the glass, okay, so and when you remove this excitation from the other side, you excite only from one side, you again see the return of the defect emission and the reduction in the main peak emission. What this is telling you is that you have an exponentially decaying absorption profile in your perovskite film. Okay? This is true with any semiconductor, nothing specific about perovskite. But this exponentially decaying absorption actually results in a exponentially decaying generation of charge carriers. So you generate more charge carriers at the surface than inside because you absorb less in the depth of the film than the surface. Okay, so if you basically excite from both sides, you are generating more on both sides of the surface, not just on one side. In this case, you are generating more charge carriers here and less at the back side. So there is a gradient. Here you are generating more at the back, even at this side of the sample. So the generation of or the balance of generation of charge carriers is very essential. So it tells you that if you manage to illuminate your perovskite film from all sides, not just from one side, probably you can reduce this effect. Okay, and that is something we can see here. What we observe is, if you look at the top graph, if you make your sample really thin, okay, the sample is so thin that the difference between front and back is very less, then what you see is the defect emission is always there from the beginning. There is no rise and saturation. Okay, the defect emission is always there because it is so thin that the front and back hardly matters. It's the same. But if you make your sample very thick, so that you have a thick semiconductor sample, you have very high absorption on the front surface, back surface very less. If you excite from one side, you will see that the emission of the sub-band gap defect increases with time and then saturates, whereas the emission from the main emission peak reduces slowly. Okay, this is what you observe. The same thing is observed here. What we tried to do was to observe how thick is this effect dominating. Okay, so we change the thickness of our perovskite, and what we observe is the difference between the PL from the front and from the back. So you excite from the front, collect the photoluminescence, then you excite from the back, collect the photoluminescence from this perovskite, and take the difference between the two. If there is no difference, you will have a zero value because the PL from front and back is the same. If there is a difference, you will see a difference here. So what we observe is, as we increase the thickness, there is no difference in the PL until 100 nanometers. Okay. Beyond this, we basically see a big difference in the PL obtained from the front and the PL obtained from the back of the sample. Okay. So you can see that up till 100 nanometers, this defect formation sort of dynamics are happening all throughout the film. Beyond this, it only happens on one side, not on the back side. Okay. So 100 nanometers seem to be key thickness to achieve those sort of parameters. Now, we did some ultra fast investigations on this, and for people who don't know this, don't worry, it's nothing that you need to really get in depth about. What it basically shows you is, with time, when you excite your sample with a laser, you switch on your laser and switch it off. When you switch off your laser, your excited charge states should relax down to the ground state. Okay. So if you excite an electron to the conduction band, when you remove your laser, when there is no excitation, that electron should come back to the valence band. Okay, relaxed down. So that relaxation process can be actually physically seen, and this is what it is. So you excite with a laser, you form many charge carriers, and you relax over time, and that happens at the same wavelength, which is the band edge of your semiconductor. So this is a sample with 60% iodine, 40% bromine. So you can see, without any background sunlight illumination, if you create charge carriers, the charge carriers recombine at the desired band edge. Okay, the relaxation is there, straightforward, no deviation. But if you illuminate your sample with sunlight, what you get is this. So what you see, originally we saw that the excited charge carriers were relaxing at the same energy level with time. So it's a straight line we saw in the earlier graph here, straight line. What we see here is not a straight line. If you illuminate with sunlight, you see that you start creating some other states here after certain time. Okay, and this time difference between these two is around 9 picoseconds. So 9 picoseconds is very small value. Okay, 10 to the power minus 12 seconds. So it's very small value, and with that fast rate, these charge carriers which were created here are going into this state here. which is your so-called defect level. Okay, that you can visualize here. If this blue curve is signifying the excitation, and you switch off your laser here, and the charge carriers decay. Okay, this is a normal thing. But what happens is that when your charge carriers decay, you also see a rise in the charges at the defect state. And this indicates a charge transfer, okay, energy transfer effect. But what also happens with this effect is the PL quantum yield of the defect emission is actually increasing with time. And you see, if you keep illuminating your sample, of course, you will get an emission from the defect state. But that emission is very efficient. The emission is almost 70% efficient. So you can see that the emission from this defect is almost radiatively efficient. 70% of charge carriers are recombining radiatively. And this is something you can use for LEDs. Okay, not useful for solar cells, because in solar cells you're losing your voltage. But here you're getting very efficient LED kind of material. I'll tell you a bit about it later. So how can we stop this segregation, or let's say the defect formation and all? There are different solutions. Okay. One of the solutions is cation doping. So we believe that in the perovskites there are some vacancies on the boundaries, okay, grain boundaries, and these vacancies can be passivated. So what we do is, by passivation, in the passivation sense, is by adding potassium halide salts, we can passivate these grain boundaries. So here is one example where you have potassium halide salt, and you can sort of see a cartoon of passivation. Now, one thing we observe the same thing in the specialized TEM images. What we see here is the grain boundaries. If you focus on the laser pointer here, the factor 2, which I'm showing you here, this is showing you the segregation of potassium. Okay, you can see the potassium is segregated along these grains. The faint images, I am not sure if you can see them in your screens, but these big lumps, at least this is a big impurity, and you can see the potassium is segregated here, here, or here, and these are the spots where you basically had less halide, or let's say more halide vacancies. Okay, that is shown in the factor 1. And this sort of segregation is then helping in stabilizing the perovskite, which otherwise had a PL shift, as I showed you before. Okay, the PL from main peak reduces, defect PL increases. But when you add the potassium halide salt, you basically have a PL which is very stable. Okay, so that's what is happening here. Now, that happens with most of the mixed halide perovskites. When you stabilize the band gap of your mixed halide perovskite, the direct effect should be seen in the voltage, and that is what you see here. So you see your control samples, this black curve is giving you this solar cell performance, and your voltage from your passivated sample, where the dynamic defect is not there, is giving us very high voltage. Okay, the same is seen here, and that is what gives you also very good performance. So you get almost 21% performance with these samples, whereas the unpassivated samples could give you only 17% efficiency. Okay, so that is one example. The other example of such, prevention of such defects is to work with nanocrystals. If you make a perovskite nanocrystal where you have 66% iodine, 33% bromine, what you see is that neat nanocrystals with no passivation, nothing, just controlled nanocrystals. With time, you start seeing emergence of a new defect peak. This is same as what I showed you earlier. Okay, it is a bit difficult to get these nanocrystals form these defects than the thin films, but it does happen, as you can see here. So the defect is there. But when you passivate these with these salts, which is ethylene ditriamine or glutathione, you see that this passivation results in the PL to stabilize. Okay, now the PL doesn't shift, it's quite stable. With such passivation, you basically end up getting really good LED performance. Okay, we use this for LEDs, and these LEDs were the state of the art. This paper was just published a few months ago, and where we measure LED efficiencies of around 20%. Okay, the previous best was around 3 to 4%. So you can see by stabilizing the band gap, you can get really high efficiencies and very stable as well. This emission doesn't change; it's very stable for almost 5 hours. of continuous operation. But in displays and all, these LEDs will be pulsed, so this stability will be extended very long. Okay. So this is one of the state-of-the-art results that we achieved by such stabilization. Now, the interesting thing is, how do you basically know? You know that when you are photostable, your performances are bad and all. You know that, and you know your aim is to make it photostable. But how do you know where you are in this journey? You can do various tricks, but you need to know where you are. Are you closer to being photostable, or are you still closer to not being photostable and all? So one interesting experiment we did was this, where we basically excite the perovskite, which is mixed halide again, 60% iodine, 40% bromine. But what we do is take a PL emission spectra at different time intervals. So we took one emission at 0 seconds, one at 5, 10, 15, 20 seconds. What we observe, which is interesting, is this is the emission from the main emission peak, okay, this red one here. That emission goes here at 5 seconds, then it comes back, then it goes back, and eventually it ends up here, okay, which is the defect peak. The thing I wanted to tell you is this happened because we were almost close to the resonance frequency of this defect formation. Okay, so you can basically change the repetition rate of your laser, which will then match the resonance frequency of your defect formation. If you have done good job, you will basically see that this resonance would tend to very large frequencies or very small frequencies. Okay, very small in the sense almost as if it's continuous illumination. But anything in between means you are still not close to being photostable. Okay, so this resonance frequency is something which you need to measure. So here the frequency is around, let's say, 20 seconds. So this is the frequency we get for this resonance. And when you become completely photostable, you will just see a straight line. There will be no change in emission at all. Okay, so this is what it is. Now, that being said, the funneling effect or the increasing photoluminescence quantum yield actually has inspired a lot of other perovskite systems, where this effect is used to basically design new perovskites to make efficient LEDs. Okay, so one such system is this, where you have multiple band gaps intentionally introduced into the perovskite film. So this is a 2D 3D perovskite which has multiple band gaps, where all the charge carriers go to this lower energy band gap, like what happens even in the defect. When defect forms, all the charge carriers go to the defect and it becomes very bright. And this concept has been intentionally used here to make very good LEDs. Okay, uh, with around 20% efficiency. This is a green LED, right? So the summary of what I just spoke is basically this: that band gap engineering is a very easy thing to do. You can change the band gap of perovskite, but getting a stable perovskite is sort of a big hassle. And dynamic defects is something that forms, which opens up really interesting science questions. We also saw that nanocrystals or nanostructures of perovskites can be passivated, and the dynamic defect properties can be eliminated compared to their bulk counterparts. I also talked about the surface passivation both for passive defects and dynamic defects, and how does it lead to a stable mixed halide perovskite, which you can use for either solar cell or LEDs, two applications I showed you. So I would like to acknowledge quite a few people. So there are quite a few people who I collaborated, worked with. Currently, my group members and a lot of partner institutes, a lot of funding bodies. So I thank all these people and the funding bodies and institutes. And that's all I had for you today. So I'm open to take questions. So thank you.
Okay, thank you so much, Dr. Aditya, for such an informative talk and providing some deep insights on connector solar cell engineering for uh, having higher efficiency of the solar cells. Okay, so now the platform is open for the audience to ask questions and interact with the speaker. There are a few questions in the chat box. Dr. Venkatesh Hatavar has asked whether this perovskite material is stable for the application purpose.
Whether this material is stable for application purpose. Yeah, so the main challenge is stability at the moment, and of course, these materials are getting increasingly stable. So the potential of putting them in commercial applications is definitely approaching at the moment. With almost there are quite a few companies in solar cell field which are currently developing very high stability perovskite modules for solar cells, and with very long stability, very impressive stability values. So that sort of tells me that of course these materials can be stabilized and they can be application worthy quite soon.
Okay.
So I can
Professor
also,
Rani has
yeah.
asked up to what temperature the perovskites are stable.
So this actually depends on the perovskite itself that you want to focus on. So the methyl ammonium triiodide perovskite is stable up till 120 degrees, because at 140, above 140, the methyl ammonium actually vaporizes. So you are left with only lead iodide, which is not a perovskite phase. But as compared to that, if you change the cation like formamidinium, you can get stability up to 180 degrees. If you use cesium, you can get stability up to 300 degrees. Nowadays, there are perovskites which are made out of chalcogenides, and they are stable up to 1000 degrees. Okay, so the stability actually depends on the kind of perovskite you choose. The only hassle is that all perovskites have not been optimized to perform to the same efficiency. So that optimization has to be done, which we believe can be done because of the intrinsic nature of defect resistant or defect tolerant nature. But yeah, the temperature stability actually depends on different perovskites in the range of 100 to almost 1000 degrees.
I see. Okay. Diksha Prabhugavkar has asked, can halide segregation be overcome by choosing appropriate A site cation?
Yes, yes, indeed. I mean, I just showed you what I worked around. But if you go to the literature, there is a lot of literature around cesium-based halide segregation prevention. Okay, so if you add cesium to these mixed halides, cesium as one of the cation, they have observed very good defect tolerance or halide segregation tolerance. So yes, you can change A site cation and achieve halide segregation prevention and overcome that.
Okay, Delilah Martins has raised the hand.
Okay. Hello, sir. Am I audible?
Yes, yes, I can hear you.
So I had a question regarding you have used potassium halide salts to passivate the defects, right? So I wanted to know under what basis did you use only potassium halide salts? So can you use like something like rubidium, something like that?
Yeah, so the reason we use potassium halide salt was very simple at that time. The reason simply was that potassium halide salts are easily available. If you go to rubidium, the hassle is rubidium is a very exotic metal. It's not available with that same percentages as what potassium is available at in Earth's surface. So if you develop some strategy to overcome some difficulty in perovskites, let's say in this case the halide segregation effect, what we also need to keep in mind is we need to develop some method which is adoptable by the industry. And that was one of the motivations why we only choose potassium. But we also have been experimenting with sodium per se. Rubidium, yes, indeed, adding rubidium also stabilizes the perovskite to quite a lot of extent, but that is not viable for use in industry. That's the only hassle because of the cost.
Okay, sir. Thank you, sir.
Thank you.
Okay, thank you, Aditya. Uh, I have, okay, there is another question by Mayur Patil. What is the maximum efficiency achieved by perovskite solar cell? Are perovskite solar modules available in the market like mono and polycrystalline? Silicon cell, I mean, he wants to
Right.
say.
So the maximum efficiency that has been achieved with perovskite single junction is around 24.5%, something around that. That is single junction in a perovskite solar cell, which is polycrystalline. Monocrystalline perovskite solar cells have yet not been made. This is all that we talk about. Perovskite solar cells are all polycrystalline. Okay, so polycrystalline solar cells are the one that people are trying to bring to the market. The technology that will come to the market is not a single junction polycrystalline solar cell. It will be a tandem solar cell with silicon, which will have silicon plus a perovskite, and which will increase the efficiency of silicon from around 24-25% to almost 30%. Okay, and that will have a polycrystalline silicon on top in the tandem configuration.
Okay. Uh, if there are no more questions, I have a very general question for you, Dr. Aditya.
Yeah.
It's mainly on behalf of the audience, I would say. Many
Yes,
among
sir.
the audience may not be aware of this. What are these perovskite solar cells? For some, it may be a very new term. So, and they are so hyped over this silicon solar cells. So, what are the simple plus points you can tell the audience of this perovskite solar cells? Why they are so famous right now in the material science field?
See, the reason why perovskite solar cells are famous is the simplicity of making it and the cost of making it. Let's say you want to make a silicon solar cell. You cannot grow silicon everywhere. In fact, in India, we don't even grow silicon in the first place. If you talk about silicon solar cells, then in India at the moment we don't grow our own wafers. We import the wafer and then that silicon wafer is processed into a solar cell. So the raw material does exist. We have a lot of sand, but making it into a pure silicon ingot, cutting it into wafers, that part is not at all done here. We import all our silicon wafers, even for research or for industry. Okay. But perovskite, on the other hand, the materials are available as salts. So we use salt for a daily cooking purpose, like sodium chloride. It is similar to that salt, and all that we do for making perovskites is add two salts, which is methyl ammonium iodide, lead iodide, for example. These are like your sodium chloride salt. You mix it in a solvent, which happens to be DMF. Instead of salt mixing in water, you make a solution in DMF, and it's as easy as spin coating or spraying your perovskite on top of your film, and heating it to 100 degrees. Okay, this itself will give you a very good polycrystalline film. So it's as easy as the way I am speaking actually. So it's not tricky. The only trick is to avoid defects, to improve the quality of these films. That is where you need to put in some efforts. But making a perovskite is very simple and it's very cost effective. So you don't need a big fab plant, a $1 billion plant to make silicon. You can make perovskite, I mean, in your lab very easily. If you just have a fume hood, basic protection to avoid any lead contamination, you can basically make your perovskite very simply on a very large scale. So this simplicity and the availability of the material and ease of synthesizing these perovskites is what makes it very famous. And that's one reason why you would find at least one research group in every university across the world. In IISc where I work, there are at least 6 research groups who work on perovskite. I'm sure at your place you have quite a few. So you just multiply the amount of manpower that is working on perovskites, and that is
Right.
leading to such sort of progress. But silicon, because we cannot make our own silicon, we cannot make solar cells, we cannot really progress much further. Although the field is already progressed, but the ease of using, making, or doing research on perovskites is the attractive feature. Yeah.
Okay. So finally, a concluding question.
Sure.
Since you are a very young scientist and kind of inspiration to the students who want to choose research as their career, what will be your take-home message to young research students?
Take home message. Well, if if I go through my journey as a researcher, when I entered PhD, I'm assuming most of the people here are either MSc or PhD students. So when I entered research domain, I entered with a very open mind. because my research is very interdisciplinary. If you see, I have been an engineer, I'm an electronics engineer. My actual specialization was in automation, which means I actually used to design baggage handling systems for airport. If you go to airport, you give your bag at your check-in counter and that reaches the flight. You get your bag when you land somewhere. What happens when you put your bag at check-in and the moment you get it at the airport at the other side, the baggage handling systems that you have in between, which you don't encounter, was something which I designed. Automation was my job. Then I entered nanoelectronics due to curiosity of learning nanotechnology. But later, when I entered physics, where I studied about solar cells, the interesting thing was being open minded, but at the same time, being a bit persistent as well. So, what happens generally is you might get very worked up or very frustrated when you don't know or don't understand different things. You might not believe, for one whole year in my PhD, I used to sit and wonder why I'm doing PhD. But it took me time and persistence to basically understand the key principles or key literature or things, words, terminologies in my area, and then I basically picked up in the field. So that initial phase of effort is very important. Once you put that effort, then you will succeed in your research. Beyond research, it's up to you. I mean, I chose to come here in India and be in academia, but my interest is also in commercializing technology. So that is one reason why I'm at Sense, because it's very good at commercializing interdisciplinary technology. So maybe let's see what holds in the future. So for you guys should be very open minded. You end of research is not an academic job always. You need to actually look for other avenues which are very commercially attractive and very important for a country like ours. So that is what I would say. Keep your open mind, not just while doing research, but also about career opportunities after research. So that will be my advice.
Okay, Dr. Aditya, this is Dean Professor Verekar.
Yes.
Thank you very much. I was listening to your lecture. I joined a little bit late. It's a very nice lecture and learn so many things new from you. As you mentioned that you have to go for the commercialization of this product. I have solar cells on my rooftop. And they said that 20 years is a lifetime for that. So to commercialize the perovskites, how many more years India will take so that I can replace my solar with the perovskites?
Actually, if you talk about what we do at the moment, we are actually testing many modules of perovskites. So I don't see that day quite far. It would be maybe 1 or 2 years where you would see perovskite in the market. The kind of stability that you will get might not be 20 years, it might be beyond 10 years. But then beyond 10 years, anyways, even silicon, you never know how it will work. So you might purchase a panel from some vendor, but that vendor might disappear. So the performance of silicon is always a doubtful thing. Perovskite you can always replace, and the cost will only go down. They will never go up, in my perspective. So silicon will enter the market. No, perovskite will enter the market very soon. They are already in the module phases. We ourselves are testing certain modules at IISc facilities, and commercial availability I feel would be somewhere around next year. That is what I feel. But that will be in a tandem form. So it will be combined with silicon. You will see a very higher efficiency silicon perovskite tandem. That will be the first commercial product, in my view.
Okay, and what will be the lifetime, like the silicon, 20 years plus
It,
or
it,
less than?
so it depends on the design. If they design it in a way that even if perovskite becomes redundant after 10 years, then you'll basically have the same lifetime, 20 years. The only difference in that would be the promised efficiency. Maybe silicon will say you that, okay, at 20 years, I will still promise you 80% efficiency. With perovskite, maybe they
Yes.
will promise you 60% efficiency. That is the difference you will see, or 70%, slightly
Okay.
less. But it will
But
still be.
price wise will be 1/5 of the price of the solar, right?
price wise, it might be slightly higher than
Oh,
silicon.
higher
Yes,
than silicon.
if you go for silicon tandem, it is silicon plus perovskite. So you'll have a slight addition of cost, but the efficiency or the power that you produce will be much higher. Okay, so the
But
cost,
yeah,
the cost
silicon alone will
for
be
ah,
when will be the dream come true? Not silicon, sorry, perovskite alone.
so perovskite alone will happen maybe in couple of years, because even there the stability values are getting higher. So as of now, I see that people are projecting 10 years stability. Okay. Now, if that is really true and we have good encapsulation available, then I'm very sure that at least 10 years you will get a perovskite to be very stable. But the good thing about that is it's not just the 10 years that you're looking at. The 10 years is the efficiency in the external atmosphere. With perovskites, you can even use it in indoor photovoltaics. You can use it inside the house or maybe in diffused light situations like glasses on buildings, things like that. So you can use these perovskites on those areas to produce energy where silicon can never be used. Okay. So there are many other avenues which are not yet tapped. So that place perovskite is quite attractive. And indoor conditions is very controlled indoor conditions. You don't live in very harsh weather inside a house. So if you use something inside a house, then you can expect the 10 years to be 20 years in terms of stability.
Okay, okay. And then it can generate through the our normal bulbs and tube lights, whatever lights
Yes,
generate
yes.
from
So
there.
the aim won't be to generate electricity through bulb, because that will be waste of energy because
No, no,
you
no.
first
In
spend
the house,
energy. But
suppose
yes, yes.
your walls are having that
Ah,
layers of perovskites, then
yes, yes. So you can basically generate. I mean, the right terminology would be reuse or sort of recycle energy
yes,
indoors.
yes,
Because currently we don't do. If a light is on, it's just on. You either
yeah.
make use of it or you can switch it off. But you don't really reuse the energy that is going through the light. So that can be done with perovskites.
So nice, so nice. Thanks a lot from School of Chemical Sciences, myself, for such a nice lecture. Of
Thank
course,
you.
Dr. Anjani must have thanks you already. In between, I was just out of the, I just missed the link. Just went out by mistake. Yeah. So
Sure.
thanks a lot. And another time we'd like to see you, maybe not this year, then next year at least, in the form of a second lecture. Right?
Sure, sure, sure.
Thanks a lot. Thanks
Would
a
be a
lot.
pleasure. Okay. Thanks everyone. It was a pleasure
Just a
talking to you.
second, Dr. Aditya. Thank you
Yes.
so much for joining us. So, if there are no further questions, I would request Dr. Diptesh Naik to please propose
Okay,
vote of
okay.
thanks.
Okay, on behalf of School of Chemical Sciences, I extend a hearty vote of thanks to our today's resource person, Dr. Aditya Sadhanala, assistant professor from ISC Bangalore, who spared time from his busy schedule to illuminate us with the very interesting and informative talk on passive and dynamic defects in perovskites. We are really enlightened with your knowledge and presence, sir. I would like to thank Professor VMS Verico, Dean of School of Chemical Sciences and Vice Deans of SCS Goa University for their enthusiastic support. A special thanks to organizing committee for support and coordination. And last but not least, I thank the audience for their active participation. With these warm words, uh, we move on to the end of this webinar. Thank you all. Thank you, sir.
Yeah, thank you so much. Thank you.
Diptesh.
Thank you, Dr.
Thanks,
Aditya.
Anjali.